atëherë po I them disa fjalë si zakonisht shqip, e pastaj anglisht edhe Urani vazhdon në gjuhën angleze. Edhe një herë po rikujtoj që seminari incizohet dhe do të vendoset në YouTube. Ju lutem shumë që ndërkohë që nuk flisni, t'i ndalni mikrofonët tuaj. Në qoftë se keni pyetje, e ngritni dorën përmes funksionit për ngritje dore që është në Zoom. Edhe kaq, nuk ka rregulla të tjera. Siç e dini, Urani është ish student I Universitetit të Prishtinës, I cili këtu I ka kryer studimet themelore, pastaj ka studiuar në Bonn, e tash e ka mbrojtur doktoratën në Lyon, në shtator. Edhe, më thënë, seminari I sotëm është I dyti në radhën e seminareve që kemi filluar në departament të matematikës, ku do të ftojmë folës të ndryshëm, jo detyrimisht ish studentë, dhe seminari do të bëhet me rregull një herë në muaj mesatarisht, me përjashtim disa periudhave, ta zënë muajin janar nuk do të ketë për shkak të afatit provime për student, por folësi I radhës do të prezantoj në shkurt datën e saktë edhe emrin e tij do ta merrni me kohë. Në qoftë se keni studentë që janë të interesuar, ju lutem shumë e qarkulloni sa më shumë ftesën që e merrni. Atëherë po filloj tashmë. Po kthej në gjuhën botërore angleze. So I am delighted, we are delighted to welcome our second speaker in the series of seminars of the math department at the University of Prishtina. The speaker is Uran Meha from Lyon, who will be talking about Plactic monoids via rewriting theory. He will be speaking for about 30-40 minutes, 45, and then we will address any questions or comments that you may have. Okay, so thank you. The floor is yours.
Okay, perfect. So first of all, I'd like to thank Chandran for inviting me to speak at the seminar. It's a very big pleasure of mine to speak at the university where I started my math education. So without further ado, I'll get into the presentation. So the title of the talk will be Plactic monoids via rewriting theory. And I hope that by the end of this talk, we will kind of have an idea of what plactic monoids are, what rewriting theory is, and how we can use this tool of rewriting theory to study the plactic monoids. So this presentation, I will basically talk how using rewriting, one can perform some homological study of the plactic monoid. And in particular, the talk is separated into three parts. First, I'll talk about low-dimensional homology via rewriting theory. Then I'll talk about some ideas from group representation theory. So these two first parts, they should prepare the setting to speak about the work I did in my PhD thesis, which will be here in the third part. And then finally, depending on the time, I can just briefly show some kind of visual combinatorics that appear in all of this stuff. All right, so let's start with the first part. So yeah, first, I also want to say that homology is a very, very vast field of mathematics, very deeply researched, but here I'm just going to try to explain some of the main ideas with some very small examples. So the general idea of homology consists of the following problem. So this should be singular homology, but we should be satisfied with this terminology for now. And the problem is, you would like to identify or count holes in topological spaces. And homology provides an algebraization of the problem. So what this means precisely, I will not exactly say, but I will demonstrate with an example. So we can consider a topological space, which is, one might also see this as a graph, which is S1. So I take two vertices, X and Y. Oh, why is this here? One moment, I need to X and Y. What do you do? Yeah, maybe I should write slightly lower because the zoom is messing up. Okay, so S1 is here. So you have this space. we have two vertices, X and Y, and we have two edges, A and B. And as said in the beginning, the question is, how can we count we would like to have some algebraic machinery that tells us in the end that we have one hole here. So this is a bit, this is a bit trivial to see, but this is a technique that works for many topological spaces. So what we do first is we write down the different data that we see here. So by C0, I will write the 0-dimensional data, which is just vertices. And these are just X and Y. Then with C1, I will denote the 1-dimensional data, which here is edges. And here we have two edges, AB. Now, in order to go to this algebraization, which I was mentioning in the first slide, what we do is we take this data here and we write it in terms of a linear map. So what we do is we look at this map here that I will soon say what it is. So D1. So here this guy is equal to just the linear combinations with integers of the two basis elements A and B. Here M, N should be natural numbers, and the same for X and Y. And here, what is this map D1 given by? So first I note that the source of both of these edges is equal to X, and the target of both of these edges is equal to Y. Now this map here, this D1, should tell you how we go from one edge to some vertices. And really the only kind of thing that makes sense here is to define D1 of A to be Y minus X, as well as D1 of B is the same thing. So why is this so? Is that really A is defined by having source X and target Y. So we just log this data into this algebraic setting. So now the question is, how can we use this algebraic way to show that there is exactly one hole there? So what we do is we compute the kernel of D1, the kernel of D1. So what does this mean? Let's say I suppose that I have an element in the kernel. It will be of the form MA plus NB. And since this is a linear map, I can break it down into these two parts, which is M D1 of A plus N D1 of B. Now I already know what the values of D1A and D1B are. So I have M times Y minus X plus N times Y minus X. And here, if I factor this out, I have the following expression. So this, since we're working in the kernel, this has to be equal to 0. Now this guy right here is never 0 because it's an element of it's a non-zero element in this free module here. So what we need to have is that this has to be 0. So we have that M equals minus N. Hence the kernel element, we can write it down as M times A minus B. So what we can say here is that this implies that the kernel of the map D1 is generated by A minus B, which I will just write as Z A minus B. And this, since we have just one generator, is the same as Z. So what have we really done here is we have figured out that this A minus B somehow is in the kernel, but what does A minus B look like? So A minus B, it looks like this. So first I follow along A, and then I follow against B, but with a reverse orientation, so A minus B. And what this, the fact that this kernel is equal to this Z A minus B really says that there's only this one hole here, which is, which we've identified. And in this case, we say that the first homology group of S1 is given by, and so this is the notation, so we have Z. So basically, we start off with a topological space and with a very kind of topological problem, which is count how many holes we have. We algebraize the situation a little bit, and when we do so, we end up finding, we just do some computations, we find the kernel, and this kernel is actually the algebraic data that says that there is one hole in this topological space. So now I'd like to take a slightly different example, but still very similar. So consider again the topological space. Let's write it with X this time. So again, I take two vertices. I take an edge here A, an edge B, and another edge C. So again, we might pose the same question. So how many holes are there? And we should, so the answer we should get is really 2 if our algebraic machinery is working well. So again, we start off by writing the 0-dimensional data and by writing the 1-dimensional data. And then we algebraize this to obtain, let me just write this. So we algebraize this and we obtain the following map, A, B, C, which is going to, again, to the vertices, so D1. And here, again, D1 is mapping A, B, and C to Y minus X, because this is the target and this is the source. Again, to compute the how many holes there are, we should compute, which I will not do as explicitly here. So we have to compute this kernel here, and if one does the necessary calculations, you'll find that actually the two holes that we have are A minus B and B minus C. So this A minus B, what again is this guy here, A minus B, and this B minus C is something like this, very similar, B and C. So this part here, so this I will call a homology basis. So I will point out that this terminology is not really too much used, but for the purposes of this talk, I've decided to call it like this, but generally it's called homotopy basis. So this is what we have. And also just to see, so we also have in this space, we have, we also have this other hole, which is A minus C, but this actually, we can just break it down into here A minus B, and then B minus C. So this, here we have a kind of union. I will not say exactly what it is, but it's some kind of gluing of the B's. And what this means is that we have, so why this hole doesn't appear there is really because it's a combination of the other two. We write like this. Okay, so as you can see, homology really specializes in finding, I mean, among other things, in finding this homology basis, which is just, you try to find the building blocks of the holes in the topological space. So finally, I'll adapt these examples just one step further. So I'll consider this space, again, very similar, A, B, and C. But here I will color this part. I will kind of fill this with a plane, and I'll call this A, like this small surface. So again, here we would like to compute how many holes there are, and this machinery should tell us in the end that we have. How do I remove this? It should tell us that we have one hole at the end, which should be this A minus B. So, but here we have a slightly different situation because we also have higher dimensional data. So again, we write down the 0-dimensional data, which is X and Y. We write the 1-dimensional data, A, B, C, and we write the 2-dimensional data, which is just A. Then we algebraize the situation, and we, but also previously I must have forgotten to say this, that since the kernel is this, A minus B, B minus C, this is the same as Z squared, which we say is the first homology group of X. Okay, so here I want to consider the same question. So again, we go to this sequence here. So here we have two maps because we have more than just one dimension. So here is Z of A, B, C, and here Z of X, Y. Okay, so here the map is D1 and here the map is D2. So the map D1 we already saw in example 2, and we know that this will map everything to Y minus X. But then we have also this extra map D2, and where does A go? So here I should kind of give A an orientation, which I won't say too much, but basically the orientation here, one might think of it as similar to how edges are oriented, which then gives a nice way to write the boundary map D1. We can kind of assume that we've done the same for A, and then what we write is we send this to B minus C. So then we go back to how many to this question to see how many holes we have in this topological space, and then what we do to compute this is we take the kernel of D1, but we mod out the image of D2. And why is that so? Because this kernel of D1, as we saw in the previous example, this had two holes, B minus C. But then this B minus C here is not really a hole. So the map D2 kind of tells us that yes, in this area here is filled, there is no hole. So what we do is we will mod out by the image of D2, which by the way that this is defined, we know that this is B minus C. And this is just Z A minus B, which is the same as Z. And so what this shows is that really this machinery will detect holes and will also detect when there are some surfaces making like closing the hole somehow. So this is the main thing I want to say with the examples about homology, that you start with a topological space here, you go to this algebraic process, and then like to this algebraic context, and then you do some computations to figure out what the first homology group is, and this should give you the answer of how many holes there are in the topological space. Okay, so now I'd like to give a bit more like a more formal discussion, not too formal, but slightly just to place the examples into mathematical theory. So what homology theory does in general is, for a nice topological space, I will not say what nice is here, but one might think of it as CW complex if and so on. We denote by Cn the set of n-dimensional data, similar to how we did in the exercises. Then from that, we can obtain, just as we did, the sequence of maps of abelian groups. So here, these Dn are the boundary maps, and the Cn are just a set of n-dimensional data. And moreover, these boundary maps, as we saw, they satisfy this condition here that the image of Dn plus 1 is a subset of the kernel. Actually, we saw this only the third example, because previously there was no C2. Then the nth homology group, so this is singular homology, but I refrained from using too many adjectives in this talk, is defined as a quotient, the kernel over the image of the kernel of Dn modded out by the image of Dn plus 1. So just to give an idea of what, so throughout this talk, I'll draw the scheme. I'll keep updating it just to kind of show what the problems are that we're studying, and how they look like in the big picture somehow. So from what we've seen, homology takes a topological space, and via homology, we're able to perform some algebraic study of the topological space. So then a natural question arises here is, can we apply these, which is very classic in mathematics, which is, can we apply this machinery of homology to study other algebraic objects, such as monoids, groups, algebras, rings, and so on? And the answer is, in general, yes. There's many different techniques to do this. Some actually, the most classical ones in homological algebra I can think of, they just take this long exact sequence of maps and they abstract the notion and then perform homology. But today I'm going to give an example of what rewriting theory does, which is, you start off with a monoid, you somehow construct a topological space and then do topology. Okay, so what rewriting theory is precisely this. It does is precisely this. So we start off with a suitable presentation. I'll say in a second what I mean by this. X, and then of an algebraic object M. So this is the algebraic object we start with. Then you can construct a topological space. So I put this into quotation marks because it's not really a topological space. It's rather a two category, which should be intrinsic to M. I will also not say what intrinsic is, but somehow one should think of this topological space as having nothing that nothing that doesn't come from M. Somehow you really construct the optimal topological space. And then the idea is that once we start off with an algebraic object in a presentation, we construct this topological space, then we apply homology theory to this topological space, which then should give some homology considerations on the monoid M, or the algebraic object M. Okay, so for us, the algebraic objects will always be monoids. And what monoids are is basically a set with an associative product and a unit for the product. So you can think of the natural numbers with a multiplication. So we don't really require to have inverses and such. Then a particular case of the monoid is that of the free monoid, which is we start off with a set S, and we look at all the words we can form from the letters in S, and we write them down, and then the product here is going to be concatenation. So we just attach two words to one another if we want to multiply them, and the unit, as concatenation suggests, is just going to be the empty word. But this monoid is nice, but it doesn't have any kind of interesting relations inside. So what we are most generally interested in is monoids that are given by presentation. So I'll recall a notion of oriented presentations of a monoid M, which is simply a pair of sets where we have generators here. So we have n generators in this case, and then we have generating relations, which are of this form. So you take a word W and you say it is the same as W prime, but there is some bias towards this guy because we're kind of orienting the equality in this strange way. And this should be seen of as when we do this part 2, this orientation here should reflect the orientation of the edges that we saw in the previous examples. So once we have generators and generating relations, we can define a monoid presented. Actually, no, once we have such a presentation, it presents a monoid as follows. We take all the free words in x1 star, and then we mod out by this congruence, which is generated from the rewriting rules. So yeah, what this says is I'll have two words will be the same, is one of them can be rewritten to the other kind of, yeah. So this idea gives the blueprint of how to talk about this topological realization of X. So what we do is we associate a one-dimensional topological space where the vertices are the words in x1 star, and the edges are how we form edges is we look at this generating relations, and we are allowed to multiply to the right and to the left to get this guy here. So that is what the edges will look like. I'll soon give an example so that all of this will start to make a little bit more sense. So now I will say what these suitable presentations are, and they are what are called convergent presentations of monoids. So to say what convergent presentations are, I will mention two properties that we want the presentation to have. So the first one is termination, which says that there's no infinite rewriting sequences given by the presentation, meaning that if I start off with a word and I want to rewrite on it, then at some point I will arrive at what is called a normal form. So this will terminate at some point. Then there's a property of confluence, which states that if I have F and G rewriting sequences, so F and G look kind of like this, like rewriting sequences, then I can always, if I have like a branching, this is called a branching. So I start off at W and I can rewrite W into two different words. Then they can always be joined at a later point by rewriting rules, which means that this thing exists. It's not necessarily unique, but it is there. And another slightly less restrictive property is that of local confluence, which states that F and G, which states that the exact same, so confluence, but here F and G are not really rewriting sequence, but are kind of like this, just one step of length one. As this guy. So if we have a presentation of a monoid which satisfies these two conditions, which is termination and confluence, we call the presentation convergent. And in particular, a notion that is relevant here is that the word for which is in its final form, so you cannot really rewrite it to anything else, is called a normal form of the presentation of the monoid. So next so the whole idea is here, just to go back to the first few examples, is that these objects like here will be the two-dimensional holes, I should call, in X top. So as we saw there earlier, the idea was how to find the homology basis. And this is what we shall see in the following of X top. So in order to do this, to say how we find this homological basis, I'll just do a bit of technical stuff, which is not too difficult to follow, I hope. So the set of local branchings, and these local branchings were just the objects of this form, F and G, where F, G both have length 1. So the set of these objects is equipped with a partial order, which says that Fg is smaller than anything that you obtain by multiplying to the left and to the right. So somehow we want to find the smallest branching, some TV, let's say, if it's like this, then I want to remove the unnecessary stuff, which here is a T and V, to just get F and G. And this here is smaller than this guy. And now the branchings which are minimal with respect to this order are called critical branchings. And why these critical branchings are important is that we shall see that they are really used to explicit this homology basis, but also they're useful in proving that the presentation that you start with really satisfies these two properties of termination and confluence. So termination, so we have these two classical results which say how to prove convergence, so how to prove convergence. We have these two results. First says that if your presentation is terminating and locally confluent, then it's confluent, hence also convergent. And we have this other result called the critical pair lemma, which says that if you want to show that your presentation is locally confluent, it suffices to show that the critical branchings are confluent. Okay, so now I go back to another example, which should illustrate everything that we've seen here so far. So I will consider a presentation where the generators are the elements from 1 to n. And the generating relations are, I just take two letters, and if they are in the wrong order, then I flip them so that they're in the correct order. So this could be like 3, 2 goes to 2, 3. And this presentation will present the commutative monoid on n generators. It's not so difficult to see. So this presentation here is terminating because the rewriting rules, they preserve the lengths of words, and also they decrease the lexicographic order. So what this lexicographic order is basically, you want the smaller letters to be in front. I will not define it exactly what it is, but the idea is this: you compare letter by letter, and the first time that you encounter a smaller letter on one of the words, you say that that word is smaller. So yeah, this presentation is terminating. To show that it is confluent from this critical pair lemma, we need to, it suffices to show that the critical branchings are confluent. So first we figure out what the critical branchings are. So they are of this form, because I start off with a word like this. So you can think of this as 4, 3, 2, for example. Then I can either apply a rule here, which brings it to 3, 4, 2, or I can apply a rule here, which brings it to 4, 2, 3. So really this P is just a kind of naive sorting algorithm. I don't think it's quite fast, but somehow the goal of the rewriting steps is to sort the word into the correct order. So these are the critical branchings, and we compute their confluence diagrams, which is not so difficult to do. So here, let's say if I'm here, there's only one place I can apply the rule, which is exactly here, because this is already good. So I apply the rule here, and then similarly for the thing below, and we get this hexagonal shape. So this is how the confluence diagrams of the critical branchings look like. And then, since they are confluent by the critical pair lemma and Newman's lemma, we have that this presentation here is convergent, which is what we wanted to see. So once we have such a presentation, there's some stuff that arises. For example, if we start off with the word 4321, there's plenty of ways you can write it to its normal form. So here I've presented two ways to rewrite this to its normal form. So one might view this image here in two ways. One is that you can see this as relations between relations, because this here is a relation, as is this guy, relation, and so on. And this here is basically, you have this one big relation here going up, and then one big relation down. So one might view this confluence diagram as a relation between relations, but also going back to the first few examples, one might see this as a two-dimensional hole in this topological space. So again, we go back to this question of how do we find the homology basis for this X top? This top, so this is precisely the question. And in order to do this, this is the work of Squire, which states the following. So we start off with a convergent presentation of a monoid. Then for each critical branching, we draw the confluence diagram of the critical branching. And then if we set X3 to be the set of all these confluence diagrams, then this will be a homological basis for our topological space. And this triple here is called the X1, X2, X3 is called the coherent presentation of M. So again, I will illustrate this with the example that we have just seen. So the presentation we saw that of this commutative monoid, that it is convergent. Then by Squire's theorem, we have here generators, we have here relations, and here we have this homology basis. And by this theorem, we have that this is a coherent presentation. So in particular, this should mean that we can fill any kind of two-dimensional hole in this topological space by the basis elements. And here I've drawn, I've explicited this on the example that we saw previously. So here we have this is a basis element. Oh, how do you write it? Be like this, basis. Also, this is a basis element. And then we have these squares, these weird squares here. But what one might think of them here is that they are really just covered with this two-dimensional surface. And the reason is that if we start off with this word and we go along the green line, what we do is first we apply a rule here, and then we apply a rule here. And if we go along the blue line, means that first we start here, and then we apply a rule here. So this square is really not saying anything useful or important about the presentation or the monoid itself, because you can always choose the order in which you apply the rules. And as is the same case for this guy. So we had this two-dimensional hole. And here we've written it as a, written in terms of the basis. Of basis, which is what we wanted to do. Okay, so again, I'll go back to the schematic representation of what I'm talking about. So we had already this homology arrow. So now I've shown that once you have a monoid via rewriting theory, and I should add here convergent presentations, we go to topological spaces, and after that we are allowed to do some homology there. Okay, so this is the first part. Now for the second part, I'll briefly give some ideas of group representation theory, because the monoid that we will look at will come really from these group representations. So the general ideas are, you start off with a field. One might think K equals C, complex numbers or the real numbers, and you have an n-dimensional vector space over this field. Then the general linear group on V is basically the group of invertible matrices on this vector space. And then what representation theory does is you start off with a group G and you try to embed, not quite embed, but you try to realize this group as a subgroup of GLV. Somehow this GLV is like the boss group, and then you try to take everything in like any group and realize it inside of there. So what this means is that if you have an element G in the group G and a vector V, then you have this notion of G, the acting on V, by just taking this element G, saying what the morphism does to it. So it takes it to row of G, and then this here is an element of GL of V, and then you just apply this transformation of the space on the small vector. So this is what the group theory representation of group theory does. I will soon give a small example just to make sure that we follow. So a key notion there in group representations is that of sub-representations, which is you look at subspace is called a sub-representation if it is fixed by the action of the group, and if the V has no sub-representations, it's called simple. So here I should say trivial, because non-trivial, actually non-trivial. Okay, and these simples, one might think of them as somehow the primes for the natural numbers. So really they are just the building blocks to an extent. Now, a cool property that we often want our representation theory of groups to have is semi-simplicity, which says that if, so for example, in the case of finite groups, if you have a finite group and you look at its representations over the complex numbers, then this will decompose into a direct sum of simple representations. So everything is built by these simple guys. Okay. Yeah, so here I just wanted to give some example. I will not go too much into this, but I will consider a group Z3. This is just a group on 3 elements now, and it's two-dimensional representations. So in order to look at the representations of Z3, we need to have let's over C, I will say, over R, let's say. These representations are V. So what we need to have here is we need to have an action of 0 on V, of 1 on V, and of 2 on V. So this here will always be the identity, because the representation is a group homomorphism. So this will be the identity always. This will be whatever it is. We shall soon see. Everything is determined by this guy. And 2 acting on V is the same as 1 plus 1 acting on V. So really all we need to understand is how 1 acts on V. And since 1 acting on this vector space of 2 dimensions is determined by the generator, we can just assume 1 acts via some matrix, via, let's call this, so I'll just write maybe some easy matrix. This is sine 2 pi over 3 and minus cosine 2 pi over 3. And then what this does to the plane is, you can think of this as a 2-dimensional space, 0, x, y. Then as I assume some people can already see, this will just rotate this square here. So let's say I write it with S. Then if I act with 1 on this S, I will just rotate it by 120 degrees, which I think might look something like this, if my drawing skills hold up. So this is 1 acting on S, and then similarly we have this has to be a square, 2 acting on S. So this is what representation theory does. We have this very small group which has 3 elements, and we manage to realize it as some transformation of the space. Okay, so I'll give another example just to illustrate a similar kind of just to illustrate a key concept that we shall see soon. So again, we have Z acting on V, which is a two-dimensional vector space. Again, using the same analogy, since this is a cyclic group, its action is determined by the action of the generator, which we assume that, let's say I will take an example, 1x on V by the matrix 3 minus 1 minus 1 3. Now, why I take this example should become clear soon. So again, I do this square thing because I want to see what the action does here. So yeah, if we really just multiply with the matrix, we shall see that this vector here is mapped here, and the vector here will be mapped to some guy like this, and then I draw this parallelogram. Now, what one can spot here is that this element here will really, like the vector, the sum of the two basis vectors will be mapped to the longer one, and the same is said to is true for the other. So let's say A10 plus 0, 1 is it's going to be lambda times this vector u1, let's say, and then same for u2, which is this guy here, is going to be lambda 2 u2. So why this is important is that sometimes representations will fix some basis of eigenvectors, and in that case, for us, it's very convenient to write down the space, to decompose it into these two parts where we know that the group or whatever the object is will act on the eigenspaces, will act on some basis elements by some eigenvalues. But also I want to say, note that this is a more general situation. These are not always this is a more general. So the idea is we try to find these to write down the vector space in terms of its eigenbasis, and yeah, this idea will show up in a second. So now I will specialize a little bit the representation theory to the simple Lie groups. So we consider G to be a complex simple Lie group of classical type A, B, C, or D. Then, for example, this might be, the notions might not be too familiar always, but G for type A, you can just think of it as being the special linear group over the complex numbers. So just some kind of group. And these are the matrices whose determinant equals 1. And then, this part is a bit hard to really go into depth on, but the idea is that to study the representations of G, oftentimes you associate the Lie algebra, which is small g, so that the representations are pretty similar. So I will not say too much about this, but whenever you see small g, you might just think of big G as well. It's not too important for this talk. So then what we can say about the representation theory of G is that we have the semi-simplicity, which states that every representation can be broken down into direct sum of simples. And we have a weight decomposition, which states that, we can take a V representation and break it down into these generalized eigenvalues, which are called weights. So again, like I was saying earlier, this doesn't have to be a sub-representation. It's just a way to find a nice basis to talk about your action. So what is important here is that the set of weights for the representation V of G is denoted by this WT of V. And then we have a basis, and we specify a notation for the basis element of this weight decomposition. And what's interesting is that this set of weights admits a partial order, and moreover, V is entirely determined by the highest weight in this set here. So really, the weights are just a way to characterize the representations of the of the given Lie algebra. And moreover, this set this basis B of E, it admits a directed labeled graph structure, which is called a crystal. So yeah, what we should think of here is that we start off with V, the representation, and we extract from it these two sets, which is the weights and this basis here. And somehow these two should contain all the information that one has about that one needs about the given representation. And this set here admits this graph structure called the crystal, which I will illustrate here with an example. So for GSL3 of C, which we then go to the Lie algebra, representation like this skeleton of this representation here would look as a graph here. And here the edges, the labeling of the edges really just tells how you go from one basis element to another by multiplying with some, so here we would have V0, and here E2 is just an element of the Lie algebra. So really this is, if we have this crystal drawn, then we know exactly how the representation will look like and how the action of the group or Lie algebra looks like. And one key thing to notice here is that the vectors which are on this leftmost side are called vectors of highest weight. So those which have no edges entering them, they are called vectors of highest weight. And these are pretty crucial because yeah, once you have a connected component, this usually tends to be, once you have a crystal, this tends to be unique. And then from this, you can really understand a lot about the representation. Okay, so now I will say what the Plactic monoid is. I guess it's about time. Yeah. So we have seen some representation theory of groups, and we have seen this when we were talking about simples and semi-simplicity, the direct sum, but there's also this other operation, which is the tensor product. And generally, the tensor product is more difficult to understand than the direct sum, especially the action of the group or of the Lie algebra. And in particular, if you start with two simple representations and you tensor them, it's difficult to know how this tensor breaks down into direct sum of simple presentations. And one way to kind of attack this question of understanding the tensor product is to encode to encode the representation theory into a monoid, which is precisely done by the Plactic monoid. So this is just a monoid where the elements correspond to the basis vector in one of the weight spaces, and the product of two elements corresponds to the I should say basis vector in this guy here. So really what the Plactic monoid wants to do is to have one element for each basis vector of a representation, and their product should model the tensor, what happens when you tensor the actual representations. Yes, precisely what I'm saying. And then one cool thing to note here is that the crystal structure of the representation will extend to the Plactic monoid. So this Plactic monoid now has many different points of view. So one is this just as a monoid with a set with some product, but also it carries inside this crystal stuff, which is very crucial for the representation theory. So now I'll update this scheme a little bit. So we have a simple complex Lie groups, and then via representation theory, we get to Plactic monoids, and then we can do some homology here. And then there's a question of this crystal, does it extend as well? And this is one of the questions that I had to treat in my thesis. And here by this, I will just say that you get Plactic monoids. Okay, so yeah, I get to the last part of the talk. So we have a notion of Plactic monoids, which are defined in this very algebraic context with representations and so on. And but this is still a monoid. And we saw in the first part of the talk, or second, yeah, that we can study monoids if we have some nice presentations of them. So what's interesting about these Plactic monoids is they also admit a very combinatorial realization in terms of their elements are parameterized by what are called Young tableau, and the product is encoded by something called Chenstedt insertion algorithm. I won't go too much in the combinatorial realization. Maybe just at the end I'll show some examples. Yeah, in order to, but if so, we have this monoid, and we want to study its, yeah, to do some homology theory there. And in order to do this, we need via rewriting theory, we need some nice convergent presentations of monoids. So luckily, this in the work of Kane, Gray, and Malero, they introduce finite convergent presentations, which are called column presentations for the Plactic monoids. Let me write PLG of classical types A, B, C, and D. So for these groups that we've seen. Here, I also note that these presentations tend to be quite nice to work with because they're almost quadratic, meaning if I start off with 2 generators, then so all the relations are of this form. I start off with 2 generators and I rewrite them to a word which has length at most 2. Okay, so what I did in my thesis is to see whether this rewriting, if we take into account the crystal structure, whether this simplifies the task of finding a homology basis. So what we, for Plactic monoids, so what I did is first I introduced a class of crystal presentations such that, so you have a presentation, both X1 and X2 are crystals. And moreover, the second condition basically says if I have some edge like this, and I draw the crystal of this guy here, then the guy on the right side will have the exact same crystal. And moreover, you will have relations here as well. So you, rather than just identifying 2 elements with each other, you identify whole crystals with one another. And then, we have this theorem which states that if you start off with a crystal presentation, then the homology basis, which is just a set as we saw in the very beginning of the talk, is also going to be a crystal. And since it's a crystal, it is really entirely determined by the highest weights. So what this means is that, if this is the highest weight, then all we need to know is how we rewrite here. And if we know that, then we'll be able to figure out the rest of the homology basis. And why this is applicable here is that the column presentations are also crystal presentations. And to figure out their homological basis, we just need to do some considerations at highest weight. So I'll illustrate what this means. Let's say I have a critical branching and I want to compute its confluence diagram or the homology basis somehow, but maybe this is too complicated. So what we do is we look in the same crystal, we go to the highest weight, which is what the 0 here signifies. So we go to highest weight, and then we complete this, we compute how the confluence diagram looks like here. And then finally, we lift back up via the crystal again. So really, this is what the crystal does. And then here we compute, and then again, crystal. So this really simplifies the task, but still at its heart, this problem of computing homological bases is very computational. So the computations here at the highest weight are also not too easy to do, but they're slightly easier than doing it for the whole thing. So so as I said, so to compute this homology basis, we need to compute stuff at highest weight. And for this, in my thesis, I introduced combinatorial tools in types A and C, which parameterize the words of highest weight. Basically, it is a model for words that appear here. And moreover, it allows to compute rewriting rules, which is via these tools. I can compute, if I start off at this word here and I apply a rewriting rule, I know exactly what this guy will look like here. And so using this combinatorics of Yamanouchi trees, so this is what I call them, we obtain the following 2 results. The first, which is also a theorem of Agen-Malbos, proved using different techniques, shows that this homology basis for the Plactic monoid of type A will again have this hexagonal shape. But for type C, which I haven't really said what it is, but you can just think of it as a kind of different Lie group. then there we have slightly different basis elements, which look precisely like this. And now to finally kind of conclude, I would like to say, just update the scheme a bit. So in my work, I show that this crystal really extends to the whole scheme that we've seen here. And then, so the fact that we have this crystal, this reduces the homological study of Plactic monoids. And in this reduced context, we apply Yamanouchi trees to perform computations. So reduces it to Yamanouchi computations. So that's pretty much all I wanted to say. The rest is just some combinatorics, but yeah, maybe we don't have too much time. But yeah, maybe I'll just skim super fast. So
I think Uran, I think that's actually a good place to stop, because
okay.
we can ask if anyone has a question.
Perfect.
So thank you so much for this very interesting presentation, and of course there were quite a few details in some instances, and I hope that those who have seen this type of material for the first time do not get discouraged, but this is a fascinating field. Does anyone have any questions for Uran? I have a question for you, one, so that I can maybe encourage others to ask you questions. You mentioned in your final the results, you mentioned types A and C, right?
Yeah. Yes.
But not B and D.
Yes.
And I mean, in some of the problems that I worked with, usually treating the case D helped me then get B and C by a technique called folding, and so also D is simply laced as opposed to B and C.
Yeah, sure.
So why is it that the B or C are easier than D? Or have you tried to look at D, or what's your approach?
Yeah, so it's a very good question. So the reason why I did C really is that these Plactic monoids, they admit this combinatorial realization, which in type A, you really have, I'll just go here. So in type A, you have letters from 1 to N. And in type C, you have a little bit more letters when you want to do this combinatorial realization of the Plactic monoids. And in type C, I just thought that the combinatorics was slightly easier compared to B and D. And also in the works that have done this combinatorial realization of the Plactic monoids, types A and C are treated at the same time, and B and D are treated separately from them. Because I think from this point of view, if you want to have a combinatorial realization of the representation theory, it turns out that B and D have some oscillating kind of notion of tableau, which doesn't quite appear in type A and C. So I just thought it was simpler, and it's kind of what the problem that was presented to me in my PhD. So it's what I worked on. But yeah, it's a good question.
All right. So thank you again. Does anyone have any questions? Don't hesitate. You know. So if you want, you can switch to Albanian or to French, whichever is your favorite language. So if no one has further questions, I would like to thank Uran again, and we do give you, a virtual lab. So thank you, Uran. Faleminderit shumë. Faleminderit gjithëve. Në qoftë se keni ndonjë koment, shtesë, lutem mos hezitoni. Faleminderit shumë, Uran.
Faleminderit.
Faleminderit, Uran. Faleminderit shumë.
Faleminderit.
Faleminderit, Uran.
Faleminderit, Uran. Okej. Shumë, po mirë që po shoh prapë shumë fytyra të njohura, edhe do të shihem së shpejti me disa prej jush. Kështu që faleminderit gjithëve për vëmendjen. Faleminderit të profesorit Qamel, faleminderit gjithëve për vëmendjen, edhe me qenë se është seminari i dytë edhe i fundit për këtë vit, urime gjithve viti i ri edhe mirupafshim në vitin 2022. Faleminderit shumë Uran, edhe shihemi.
Faleminderit gjithë, faleminderit.
Faleminderit gjithve.
Faleminderit edhe urime të gjithëve.
Faleminderit.